Okay, so in this recording, we're going to learn a basic technique for solving first-order linear differential equations. This will be about as deep as we go into solving differential equations in this course. But it's still, well, maybe not still, it is a useful technique to know when you encounter certain differential equations. So to motivate this technique, maybe consider the following differential equation. Y prime is equal to 2x over y. And you want to find the function y that satisfies that equation. Okay. So using the notation of Leibniz, we can break this equation into pieces of y and pieces of x. So replacing y prime by dy dx, the notation of Leibniz, we have dy dx is equal to 2x over y. Okay. So now let's put our differentials and our variables, let's group them by like terms in a sense. So here, we could just say y dy is equal to 2x dx. Okay. So once we have our variables together with our differentials of the same variable, then we can integrate on both sides, and we're going to solve the differential equation. So from here we get that the integral of y with respect to the variable y is equal to the integral of 2x with respect to the variable x. Okay. So these are simple integrals to solve, right? So here we have 1/2 y squared plus some constant c1. And then over here we have x squared plus some constant c2. Running out of room, but I'm going to say that C1 minus, or C2 minus C1 is C, or something like that. Just
Professor, the camera isn't really focused. Okay, now it is.
Okay. It might go out of focus when I'm standing over here, but once I move this way, it should lighten up a little bit. Doesn't focus this. And where C here is just C2 minus C1. And then, of course, you could solve for y in terms of x, and then you get a solution to that differential equation. So what did we do here? We grouped together the variables and the differentials, and then we took integrals on both sides. So 1 second. See if this helps at all with the focusing. So this general idea here, that's the idea behind separation of variables. In order to do this, you need to, if you're given something in terms, if you're given a differential equation in terms of like y prime, just replace that by Leibniz notation. You have dy dx, and then you split the equation up into x's and y's, and then you take integrals. That's it. So in particular, to do this technique, we have, so the equation, maybe make sure it's still focused. Mx plus ny dy dx is equal to 0, where mx is a continuous function of x, and ny is a continuous function of y. So when the differential equation looks like this, we can solve it. Okay. Okay. In other words, or not in other words, when it looks like this, this type of equation is separable. And hence we can use separation of variables. So we can use separation of variables. Okay, so does this equation here, does it look like that? Well, yes, it does. So we have dy dx. So if we kind of rearrange this equation here, multiply both sides by y, move the 2x to the other side, we get negative 2x plus y dy dx is equal to 0. That becomes that. So then here, that right there is like your m of x. And then that y right there, that's like your n of y. And we have this first order linear differential equation that we can use separation of variables and do this technique that I illustrated at the beginning. Okay, so maybe do some examples. So we have something like x squared plus 3y dy dx equals to 0. This has that form. So that means we can use separation of variables and get all the x's and the y's on respective sides. So here, this would become 3y dy is equal to negative x squared dx. So if you wanted to solve this differential equation for y, so what function gives you, what is the solution to that? You can separate the variables like this and then integrate on both sides. I can just do this in my head. Well, now I'll write it out for you. So integral 3y dy negative integral x squared dx. So what does this become? 3/2 y squared plus c1 is equal to negative 1/3 x cubed plus c2, and then you can put c1 and c2 together as just a given constant. So then we have what? 3/2 y squared plus 1/3 x cubed is equal to c, and that's the general solution to that differential equation. Again, provided you're comfortable with integrals, this shouldn't be too bad. So what would be like another example? I can squeeze one in right here. So like xy prime over ey plus 1 is equal to 2. Now that definitely doesn't look like this, but if we can make it look like that, then we're good. So let's see if we can do that. Yeah, so from this equation here, I can rewrite this as 1 over e to the power y plus 1 times dy dx is equal to 2 over x. I just divided both sides by x and I replaced y prime by dy dx. So I'll write it like that just so you can like explicitly see it. We have negative 2 over x plus 1 over e to the power y plus 1 dy dx is equal to 0. And if I just like rearrange all that, I can make it look like that, which then that looks like that. We can use separation of variables on this differential equation and solve for y. Which, by the way, I might as well. So what would that look like? Yeah, it's just 1 over e to the power y plus 1 dy equals 2 over x dx. And you would integrate on both sides. Okay, so that's the general technique. I'm going to go ahead and pause the video, clean the boards, and do like 2 examples, and that'll be it for this recording. Okay, so I thought I had 2 problems for us to do, but I really just have 1 ready for us, which is to find the particular solution of a differential equation using separation of variables given an initial condition. So recall that a differential equation in general will have a family of solutions, and will have a particular solution when you have an initial condition that enforces what the constant of integration is. So here we have this differential equation subject to this initial solution, or not solution, initial condition. We see that it is of this form. So we're going to use separation of variables to solve for the general solution of this differential equation. And then we're going to use the initial condition to find out what the constant of integration is. So immediately, my first thought when looking at this differential equation is to write the variables with exponents instead of radicals, and to replace y prime by dy dx. So I'm going to go ahead and do that. So I have the x to the power 1/2 plus y to the power 1/2 times dy dx is equal to 0. Make sure you can see that. Okay, so then I'm going to group my variables and my differentials together. So I'm going to subtract x to the power 1/2 on both sides, multiply both sides by dx, and I get that y to the power 1/2 dy is equal to negative x to the power 1/2 dx. Okay. So then if we integrate on both sides, so we have integral y power 1/2 dy is equal to negative the integral of x to the power 1/2 dx, which means that we get 3/2 y to the power 2/3 is equal to negative. I'm just going to combine all constants at one time because I'm running out of room We saw earlier that if we have constants C1 and C2, it doesn't matter because we eventually put them together. So this is equal to negative 3/2 x to the power 2/3 of C. Okay. All right, so I'm going to put x and y on both sides. So I'm going to have 3/2 y to the power 2/3 plus 3/2 x to the power 2/3 is equal to c. That's a general solution, but we have an initial condition that needs to be satisfied. So when x is 1, y is 9. So we have 3/2 9 to the power 2/3. Wait a minute, did I? Oh, no. Funny, y'all should have said something. Um, 1/2 plus 1 is 3/2. So divided by 3/2 is 2/3. And the power is 3/2. So I get that 2/3 of y to the power 3/2 plus 2/3 of x to the power 3/2 is equal to constant c. And then we know that when x is 1, y is 9, so we have whatever that ends up being is our constant of integration, which means that, so square root of 9 is 3, 3 cubed is 27, divided by 3 is 9, times 2 is 18, plus 2/3 of 1. Okay, so there, now you do that right. Square root of 9 is 3, 3 cubed is 27, divided by 3 is 9, times 2 is 8. Yeah, so 18 plus that, and whatever this ends up being, just plug in right there, and then that'll be the general solution. Was that 30 plus 26? 50.
56/3.
Yeah, 56/3. Yeah. 30, yeah, 56/3. Okay. So the final solution would be and then you could just eliminate all kinds of 3's here. And then divide by 2, but like give this, you see that you're getting to the exact solution. Okay. So I'm going to go ahead and say that from section but definitely read section 6.3 and then do various problems in the exercises. And that'll be it for this recording.